Hello, Mr. Luong. This is my video number 2. So here is the problem, and you can pause and read it. Okay. So for part A, I'm going to ask to draw a free body diagram of all the forces acting on Yi as she rolls down the hill. So then I'm gonna make a big dot. Okay. And when she rolls down the hill, there's going to be the force. Oh, sorry. When she rolls down the hill, Yi is going to have the force of gravity acting on her. Then she also have the force of Fn, which is going to look something like that. Okay. Part B asks, how does changing the mass affect Yi's final velocity after rolling down the hill? Use a mathematical equation to explain. So I'm going to use the law of conservation of energy to explain this. So initially she has height, but after she's going to have rotational kinetic energy and linear kinetic energy. So then I'm going to explain that. And she is a rod. Her moment of inertia will be 1/2 mr squared. And then, oh wait, I gotta write that the yeah, as like I said before, her moment of inertia will be 1/2 mr squared. And then angular velocity can be changed to v squared r squared. And then the r's cancel out. So then that becomes a 4, a 2, mgh equals to 3/4 mv squared. And then here's the important part. You can see that the m, which stands for mass, cancel out. So therefore, oh wait, sorry. Okay. So, to rewind, like I said before, the changing the mass or not doesn't affect Yi's final velocity when she rolls down the hill, because from this equation right here, you can see that mass, there's no mass in the equation. So if it's not there, then it's not going to affect the final velocity. For part C, I'm going to ask find the final velocity before Yi reaches the bottom of the hill using conservation of energy. So to do this one, I'm just going to copy and paste this part right here. Okay, so then that's how I found the final velocity. And now I'm just gonna do 4GHO3, plug that in. Her height is going to be 30s over 3. So her final velocity will be it'd be 19.8 meters per second. Okay, got it. Anyways, part D asks for what is the change in angular momentum as knee rolls down the hill. So I know that for impulse, it equals to change in angular momentum, and an impulse can also equals to moment of inertia, change in angular velocity. So then if both of these equals to impulse, I can set them equal to each other to find angular momentum. And then I know that initially she's not moving, so no initial angular velocity. And then to find the final angular velocity, I'm going to use what the final velocity I found before. So by doing this, so then to just find the final angular velocity, I just do VF divided by R, and then that will equals to her R is 15 centimeter. So 15 centimeters times 100 centimeters. .15 meters, and then so 19.8 divided by 0.15. Final angular velocity will be so then I just plug that in here. Her moment of inertia is going to be 1/2. Oh wait, hold on, I just realized something. What if instead of finding that, so I'm just going to simplify for angular velocity still. Then I can use that plug it back in here, and then you see that the R's cancel out, so then angular momentum will just be 1/2 m R VF, which equals to 1/2 41 angular momentum. So her change in angular momentum will be 60.88 kilograms meters square per second. Now, part E is asked if I, with the same mass, rolls on the same hill with a higher angle of incline, will I reach the same final velocity as me? Yes, I will reach the same final velocity at me, even though I'm at a higher angle of incline, which will make the hill steeper, but I will still reach the same final velocity, because even though I reach that velocity in less time, Yi will still reach the same velocity, because the distance makes up for the time, for the increase. So basically, I will reach the same velocity faster, but Yi will reach the same velocity slower. But we will still reach the same velocity because we are both at the same height, and it's just a matter of who reaches there first because of our because of our angle. But we will still reach the same velocity. Yes. Okay. Thank